This wheel has an equilibrium position right around here, and if released, it oscillates, and it turns out that it oscillates through about 16.5 cycles in 30 seconds. If I add a washer, this particular washer, to the system and let it oscillates much more quickly, over at nearly twice the rate. Turns out about 27.5 cycles in 30 seconds. If I add washers, if I add nuts, and I'm adding 3, you can see them there, and I add a fourth, add 4 quarter-inch nuts and let it oscillate. It oscillates faster than it did when there were no weights suspended or attached at this point, but not as fast as if I had the washer. If I do this with 4 nuts and a washer, that's the most frequent oscillation, the highest frequency. Now, from the number of oscillations in 30 seconds, I can easily determine the angular velocity omega. I did these in my head. I think they're pretty close. But of course you can make that calculation yourself. Mass of a nut is 4.5 grams. My question then was, what's the moment of inertia of the wheel? Now, let's think about the wheel. Here's the wheel at a distance of 10 centimeters from the axis. That's where we put the weights. Okay, the weights are pretty much centered at a distance of 10 centimeters from the axis. The washer, actually, since it has a little bigger hole in the middle, is a little bit lower, so it might be maybe 10.5 centimeters from the axis of rotation. We'll just assume everything's at 10 centimeters here, and everything we do initially, at least, is going to be kind of a first approximation. Okay, so here's the wheel, here's the nut. There's some torque that's causing this thing, some restoring torque that's causing this thing to oscillate. Then we're going to make the assumption that the net torque is minus k times theta. Theta being the angle of the system with respect to its equilibrium. So the angular displacement from the equilibrium position. Okay. Now we often would use kappa here with tau. I use k simply because it would have been kind of confusing, because people during the actual class were looking at a kind of a blurry picture of the board, the best we can get through Blackboard Collaborate, and I didn't want to split hairs. So it's actually often a kappa instead of a k, but kappa and k look very similar. So any case, tau net is then negative k theta. At least that's going to be our assumption, and we're going to see if we can validate that assumption. So that means, of course, since tau net equals I alpha, moment of inertia times the angular acceleration, Newton's second law, means that tau net is equal to I alpha, which is I times theta double prime, leading to the equation I times theta double prime, one expression for tau net equal to negative k theta, another expression for tau net, and we get theta double prime equals negative k over I times theta. That should remind you of something. And what that should remind you of is the equation x double prime equals negative k over m times x, the equation we get for simple harmonic motion of a mass, as opposed to the simple harmonic oscillation of a rotating system. The solution to this is identical in all aspects to the solution of the equation that we use to find simple harmonic motion of a mass, a linear simple harmonic motion along the line. And we end up with a completely analogous expression, theta equals a cosine of quantity omega t plus phi naught. I had theta naught there, but this theta would be related to a phase angle, and that would be confusing because this theta is related to the angular displacement of the rotating system. I changed that to a phi, mostly for convenience. Phi is not a real good thing to use either because phi is often your phase angle, and the phase angle would be whatever this angle is divided by omega. So it's or the phase shift. So notation isn't real great here, but still it's going to be sufficient. We're not going to use the phase angle anyway. Okay, so we get this solution. Well, what's omega equal to? Well, you go back here, and omega is equal to negative k, square root of k over I. When you get the actual solution to this equation, you're going to have a square root of k over I, where we have omega here. So again, I've got dots here. I haven't filled in the solution. It should be obvious if you understand the solution to the basic simple harmonic motion along a line. that omega really represents the square root of k over I. That just comes out of the details of the solution of the equation. So we have the relationship between the restoring force, the moment of inertia of the disk, and omega. Now, what's that tell us? Well, we've measured omega for different weights put at this point. Okay, put at this point 10 centimeters from the equilibrium position. So we know what omega is. We're trying to find I. What we need to do is we need to find K. Well, that's easy enough to do, but we'll continue with that in the next clip because this one's getting a little longer than I like to have them, although it's not nearly as long as many.